Hi everyone, this is Jude Socrates. Welcome to today's video on infinite series, where we are going to talk about the root test. We are going to cover section 2L of our textbook. And once again, if you don't have a copy, just go to the description in YouTube and you can use the Dropbox link in order to download a copy of my OER. So, just like we did in our last video when we talked about the ratio test, let's first review the two kinds of convergence that we see for infinite series. So there is such a thing as absolute convergence, where the series with the absolute values of the terms converges. The original series could be alternating, for example, or maybe in general, sometimes positive, sometimes negative. Take the absolute value of all the terms, use that to form a new series, and then ask yourself, is this series convergent? If so, your original series, is said to be absolutely convergent. On the other hand, if you do that process, but you get a divergent series, in which case it's going to diverge to infinity, but the original series still converges. Maybe it's an alternating series. You can apply the alternating series test and it passes that, so it converges. Then we say that the series is only conditionally convergent. Now, these are good definitions. In particular, the definition for absolute convergence is a great definition because if a series is absolutely convergent, then the original series without the absolute values is also going to be convergent. So this means that you don't have to test it separately. This condition is a much higher bar. If you pass this condition for the absolute values of the terms, then the original series without the absolute values also converges. All right, so with that review, let's go to our PDF and let's review the ratio test, because the root test is going to be very similar to it. All right, so in our last video where we learned about the ratio test, we are given a non-zero sequence so we can form the quotient an plus 1 over an, where now we're going to divide by 0 because all the terms are non-zero. We take the absolute value of that ratio and then we take the limit as n approaches infinity of that ratio in absolute values. You should get a limit L. If you don't get a limit L, then the test doesn't work. This limit will either be 0 or a positive number or even positive infinity. If the limit is smaller than 1, which includes 0, then our series is absolutely convergent. So notice that we don't bother putting absolute values around a sub n because part of the definition says that the series with absolute values is convergent. However, if the limit is bigger than 1, then the original series is divergent. Not just the series with absolute values, but even worse, the series without absolute values. The original series is going to be divergent. If the limit is 1, the test is inconclusive. So we saw, for example, that when we start with the p series, 1 over n squared, for example, or 1 over square root of n, the limit of an plus 1 over an will be 1. So in some cases, we know that a p series converges when p is greater than 1. But if p is between 0 and 1, the p series diverges. So when the limit is 1, we can go either way. The series might be convergent, it might be divergent, so there is no conclusion. So now I'm going to show you some magic. Instead of pausing the video so that we can switch to section 2L, my bookmarks are open over here on the side. You don't see it, but they're right here on my screen. So I am going to click now on the root test. Ready? Boom. Want to see that again? Ratio test. And now root test. Ooh, you can do it also on your own PDF. So they in fact look very similar, slightly different conditions. We want the sequence to be non-zero in the ratio test because we're forming quotients. But this time, we don't require the sequence to be non-zero because we're going to take the absolute values of the terms, and then we'll take the nth root. Okay, that's why it's called the root test, right? So what does that mean? You take a1 absolute value to the power 1 over 1, 1. Okay? You take a2 absolute value to the power 1/2, square root of a2. a3 absolute value to the 1/3 cube root. Okay, so I hope you see the pattern. Absolute value of a4, you take the 4th root. Absolute value of a5, you take the 5th root. All right, so what are we going to do? We're going to take a limit, just like we did for the ratio test. We take the limit of the nth root of the absolute value of a sub n. We should get an actual limit that exists. Again, if the limit does not exist, you should try another test. The root test will not work, and most probably the ratio test will not work either. Okay, they're almost linked together. If one of those limits does not exist, the other limit will not exist either. Chances are. Okay, so just like for the ratio test, that limit is going to be 0 or a positive number or even positive infinity. Look at these three conclusions. Shall we skip one more time? Just focus on these three parts, okay? I'm going to click it again. Ratio test. Back to root test. They're exactly the same, except for I changed one word over here because this talks about the root test. If the limit is smaller than 1, which includes 0, then our series is absolutely convergent. But if the limit is bigger than 1, our series is divergent. Same conclusions. Very good, very bad. If the limit is 1, once again, the test is inconclusive. Will it work also on the p-series? Yes, because you can prove using the logarithm method of L'Hopital's rule that n to the power 1 over n has limit 1. 100 raised to the 100th root is very close to 1. Okay, so again, the root test will not give you any conclusion. We're not going to prove the root test in the text. Aren't you glad we don't have to go over it in the video? But the last problem in my OER guides you through a proof of the root test. And let me tell you, it's very similar to the proof of the ratio test. All right, so on that, let's go back to our workroom now and let's look at a couple of examples. All right, here's our first example. We will look at the alternating series, summation 1 to infinity, negative 1 to the n plus 1, 4n minus 1 over 5n plus 2, quantity to the power n. Okay, so yeah, for the root test, we have to take the terms of our series and get the nth root. So, which is why the root test is very useful when we have series that look like this, where something is being raised to the nth power, or something related to that, as we will see in our next examples. All right, so we need the absolute value of the terms, and then we'll take the nth root. So when we do that, yeah, I almost feel silly doing this step, because when you take the absolute value there, all we do is get rid of the minus 1 to the n plus 1. Okay, so we're going to get simply 4n minus 1 over 5n plus 2 to the power n. And of course, so you know what, let me label what we just did. So we have, oops, grab it. Okay, so this is simply the a sub n. And now we want the nth root. So we want a sub n absolute value to the power 1 over n. So we don't need the absolute value symbol anymore because we already turned it positive. So we're going to take that, and then we're going to take the nth root. Okay, so I hope you remember, because we covered it in an earlier video, the rules for exponents. Okay, so if you have x to the a to the b, it's the same as x to the a times b. Do we need a refresher? X to the a raised to the b is the same as x to the power a times b. Let's put a dot over there. You multiply the exponents together. So of course, when you multiply those exponents together, you are simply gonna get to the power, oops, come on, grab it, there we go, to the power n times 1 over n, which is of course simply 1. So we get 4n minus 1 over 5n plus 2. Okay, and we're back to something that we have seen many times before. We are looking at something by which, if you take the limit as n goes to infinity, you simply look at the coefficients of the highest power, or if you must insist, you can use L'Hopital's rule. So that is the limit as n goes to infinity of 4n minus 1 over 5n plus 2. And of course, that limit is simply 4 over 5. So the root test says, find the limit. We successfully found the limit. And then you have 3 possibilities. If the limit is smaller than 1, we're in the first possibility. So according to part A of the root test, our series is absolutely convergent. Okay? The ratio, I'm sorry, not the ratio, but the root, the limit of the root a sub n to the 1 over n is smaller than 1, excuse me, and so our series is absolutely convergent. We do have a bonus example, because what we can do is follow up. If we consider instead what we get if we flip this fraction. So we will put 4n minus 1 in the denominator, and we will put 5n plus 2 in the numerator. Almost exactly the same example, except we flip the quotient. Well, that's going to flip, 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 and that's going to flip. So now we get 5 over 4 instead of 4 over 5. Okay? And so this time the limit is going to be, flip it all. We're going to take this and copy it here. And of course, the limit is now going to be 5 over 4, which is bigger than 1. So we are now in part B of the root test. Easy second example. So by part B, our series is divergent. Okay, so it goes from very good to very bad, and that's because now we have 5/4 as our limit. All right, you probably noticed from the timestamp that this video is very short compared to the others. It looks like we have the same series here, but of course we're going to change it. We're going to turn that into 5n minus 1 over 5n plus 2. So the limit of the nth root is going to be 1 if we keep it the way it is right now. Okay, so you know what? Let's write it down. Applying the root test, we will get a limit of 5 over 5, which is 1. Before it was 4 over 5, 5 over 4, now it's 5 over 5, which means that the root test will be inconclusive as is. Okay, so we're going to do something different. How about if we're going to take our series, and instead of just to the power n, and by the way, it will still be 1 if I made that 2n or even 7n or 1 million n. However, what I'm going to do is I'm going to turn it into n squared. Okay, so reminder, order of operations. This means that you compute the base, then you compute the exponent n squared, then you take the power. Okay, so maybe a reminder, this expression means, I'm going to copy it, and I'm going to put an extra pair of parentheses here. Okay, so just so you don't think that it's supposed to be, I'm going to erase that for a minute, and then I'm going to put brackets here and square there. No, no. This does not mean this. Okay? The trouble is that exponentiation is not associative. Right? So a to the b to the c, that symbol by itself, does not mean anything, because a to the b raised to the power c is not the same as a raised to the power b to the power c. Okay, you can think, you can do an easy example. 2 to the 3 to the 4, write it in the 2 different ways. You're going to get 2 different answers. Okay, so just remind you that instead of putting extra parentheses there, just keep in mind that's what it means. Okay, so we still, we want to use the root test to see if this new series with the n squared instead of n in the exponent is going to converge or not. All right, so we're going to find that limit. All right, so we want this limit, take the nth root of a sub n. So we want to take this and raise it to the power 1 over n. Now, remember what happened before. We had the minus 1 to the n plus 1. You take the absolute value, that simply goes away. So don't waste your time writing down another minus 1 to the n plus 1. I'll keep the absolute values because it will help us see that we are taking this expression, this exponential form, and then we're raising it to the power 1 over n. Okay, so again, by the product rule, now we can take away the absolute values, and we are going to multiply the exponent. I think I'm in the right level. Yes, by 1 over n. Okay, so n squared times 1 over n. So of course, we multiply those two together, and we will simply get n without the 1 over n. So it kind of looks, yeah, let's scoot back over here. It kind of looks like we're back where we started, except we're in the middle of applying the root test. We are not given a series made of this. Our job right now is to find this limit, not to see what happens to an infinite series made of these things. Okay, we're trying to find the limit of this thing. Okay, so is it time to remind you once more of something that you're supposed to recognize? Okay, remember this table? When you're trying to do L'Hopital's rule, you can only apply it to these two forms, 0 over 0 or infinity over infinity. Nothing else. If you have a product, turn it into a quotient. Difference, good luck with that. Maybe factor out something. Powers though, and that's what we have right now, 5n plus something over 5n minus something to the power n, we have a limit that looks like this. The base is approaching 1, but the exponent is approaching infinity. All right, so we have a 1 to the infinity form. Remember the process. Set that equal to y, take the logarithm of both sides, then try to apply L'Hopital's rule. Back to our workroom. There you go. This has limit 1, as we've seen before, and n is going to infinity, so we have a 1 to infinity form. Let's write that down. This is a 1 to the infinity form. Where's my infinity? There you are. Form. And so we set it equal to y. Give it a name. Y equals this thing. And then we take the natural logarithm of both sides. Okay, let's get some space here. Give me some space. And let me get out of your way here. Okay, so we are going to get ln of y equals ln of this monster. But we have our three properties of ln. When you have an exponent, the exponent drops down. So I even have to remind you of that. I will. So we get n times ln of what we have inside over here. So what's happening here? That has limit 1. Ln of 1 is 0, but n is going to infinity. So this is, which is an infinity. Where is infinity? Infinity times 0 form. So we flip one of the factors, the simpler one. So you don't want to flip this into the denominator. We flip n into the denominator and get more space. So ln of y is going to be, I'm going to make a fraction, and within that fraction, in the denominator, n becomes 1 over n. Okay, so we're going to do a backflip there, and the ln stays there. Okay, and if this feels familiar to you, we did this in the ratio test as well. Just look at the video. So this is now a 0 over 0 form, which is a 0 over 0 form. So we can apply, L'Hopital's. Okay, so, but before that though, we will, so annoying, we are going to simplify the numerator using properties of logarithms. So again, we did this last time. It will turn into a difference. So I will make a copy of this. And the first one will be the ln of 5n minus 1 minus the ln of 5n plus 2. Just the denominator, please. Okay, so we can erase this and replace it with 5n plus 2. And again, you don't have to think of this as an infinity minus infinity form, because these two are exactly the same according to the quotient property of logarithms. By the quotient property of the natural logarithm. So we can now apply L'Hopital's rule. The limit as n approaches infinity. Let's copy the limit symbol. I know we have it somewhere up here. There we go. Let's grab this. So now we have limit as n approaches infinity of this equals limit as n approaches infinity of the derivative of the numerator. So that turns into a fraction, and I'm going to borrow this. And we're going to get 1 over 5n minus 1. Chain rule times 5. And then we will have 1 over 5n plus 2 times 5. So let's copy this over here. You should all feel familiar. We did something almost exactly like this in the last video. Okay, and we are going to divide by the derivative of 1 over n. So that's minus 1 over n, squared. Okay, so n to the minus 1, drop the exponent, minus 1 n to the minus 2. And so we get minus 1 over n squared. Okay, so we're going to do some algebra now. Let's go to the next slide. We are going to distribute the numerator. So we will multiply 5n plus 2 to 5 in the numerator here, and this minus 5 by 5n minus 1. Okay, and we will combine it to a single numerator. So let's put these two numerators together. And then in our denominator, we will have 5n minus 1 multiplied by 5n plus 2, which I have over here. Oops, get back there. There you go. 5n plus 2. Okay. And then we are going to flip this into the numerator. So 1 over 1 minus n squared, that becomes minus n squared. Okay, so that goes away. And you know what? Let's simplify and get rid of that compound fraction entirely. Okay, so there you go. Quick review. 5 times 5n plus 2, right there. Minus 5 times 5n minus 1, right there. Common denominator, don't forget there's a common denominator, 5n minus 1, 5n plus 2. Flip the minus 1 over n squared in the denominator into negative of n squared in the numerator. In the last video, I factored out 5 over here or something like that. This time, let's do something different. Let's just keep the 5. Of course, we'll get the same limit. So it's really up to you what you want to do with that common factor. But be careful, of course, with your algebra and arithmetic, as usual. Distribute 5 times 5n, we're going to get 25n. And then 5 times 2 is 10. So 25 plus 10. And then minus 25n, and that's going to be a plus 5. Okay. Same denominator, and then times n, negative n squared. Okay, so now we are going to get canceled at 25n's, and the minus 25n go away. So you have 10 plus 5, 15 times minus n squared. So we're going to get negative 15n squared in the numerator, and 5n minus 1, 5n plus 2 in the denominator. So we're going to get negative 15 over 25, because we have a 25n squared down there. All right, so we have found the limit. This is going to be, I'm going to borrow that, minus 15 over 25. And that reduces, of course, to minus 3 over 5. Yay. Wait a minute. We took the absolute value. Why are we getting a negative number? Oh, yeah, I'm just pretending. Remember, this is ln of y. Okay, the limit of ln of y is negative 3/5. And remember that our y is the limit that we're looking for. Okay, so reminder, don't go away too quickly. Thus, ln of y has limit approaches negative 3/5. And so y itself approaches not negative 3/5, but e to the negative 3/5, which is a positive number. Okay? Is that a number bigger than 1 or smaller than 1? All right, so let's approximate. And yep, that is of course smaller than 1 because we have e to a negative exponent. So remember the graph of e to the x. The y-intercept is 1. E to the 0 is 1. So if you plug in a number which is negative, you're going to get a number which is smaller than 1. Plug in a number bigger than a positive number, you get something which is bigger than 1. All right, so that is less than 1. So by part A of the root test, our series is absolutely convergent. Yay! All right, so this video actually concludes all the tests and definitions that we need for understanding infinite series. In our next video, we're going to move on to a related topic, which is called power series. We're going to use the theory that we have learned so far to create series which involve a variable x, and we will use them to relate functions that we are familiar with. All right, so until then, I hope you enjoy the rest of your day. Bye.